we're going to look at the binary point, which is to say we're going to look at a way of looking at numbers that are not whole numbers. So far we've dealt with whole numbers, positive, real numbers, positive and negative, but now we've got to look at, now we've got to look at numbers that are in between values, in between 0 and 1 or whatever. So just a reminder of your number line. If we have 3,214.169, for example, all right, we actually understand what this number is. And so we have our thousandths column and our thousands column. Okay? Mm-hmm. Please don't. That's the way it works on a decimal number line. Well, the way it works on the binary number line is the same. We have ones and zeros. Now that point there is not a decimal point, it's a binary point. And we have ones and zeros and ones, and I'll put a 1 there because it's going to be really annoying. And so therefore this number can be worked out as a binary number that is between 16, 23 and 24. Okay, the reason I know it's 23 and 24, 16 plus 4 is 20 plus 2 plus 1 is 23. Point something. Now remember how we do fractions. So when we're doing our calculation in here, it's the after the binary point, all this is calculated through an addition step that we would know how to do. So we have a half plus an eighth plus a 16th. Now, do we remember when we're doing fractions, how to add fractions with different denominators? Make the denominators equal, that is correct. So 1 over 2 is what over 16?
8 over 16.
Todd, stop speaking like that. So 8 over 16 plus 2 over 16 plus 1 over 16. And so therefore that's 8 plus 2 is 11 sixteenths. So it's 23 and 11 over 16. Now, do you want to go and turn that into a decimal? Actually, you don't have to. Software design development, no calculators. If you know it off the top of your head, congratulations, but actually you don't need to. That's your answer. And it's going to be useful for you. And I know when I start thinking of examples, I have to be careful because if I don't do it properly, I will wind up giving myself a headache. You're always going to get an answer that is either a 16th, an 8th, a 16th or a 32th. You're not going to have to work out a 24th part because the binary doesn't work nicely and you start to get very, very long, complicated numbers. So we can convert a real number to its binary equivalent really easily. And if you get asked to do this in the exam, it always works the same way. Start with your number line, 1, 2, 4, 8, 10.75 or 10 3/4. Okay? And you'll be able to see that really quickly. As I'm doing this as a decimal, I'm going to do the calculations on after the binary point in decimal, whereas this one I did as fraction. So I'm going to do I did the calculations after the binary point as fractions. So what's a half as a decimal number? 0.5, 0.25, 0.125, and we actually won't need that, that is correct. So 10 is 8 plus 1. Hang on, I'll do that in a different colour.
8 plus 2.
Todd, congratulations. 10 is 8 plus 2, and 0.75 is 0.5 plus 0.25. Dot 1, 1. I don't actually need the 8th part there. So it's really, really simple. Would you agree?
Yeah.
So the decimal, like in binary or the actual decimals, how do you know exactly where the thing is, where the decimal?
Where the binary point is?
Binary point?
Well, it's not. It's a decimal number, so it's a decimal point. If I was doing this in hex, it wouldn't be a decimal point. It'd be a hex point. So, are you saying if I've got this number 110011011111 and it's a fraction, where's the binary point?
Yeah.
Good question. I will answer that. Give me a moment. I just got to get this part done first. in such a way as you can see where it's going to be. I will actually have to give you the binary point, but actually that's a really good question from margin, because when you're dealing in binary, when you're dealing in computer code, there isn't a binary point to place somewhere. It's ones and zeros. So which one and which zero denotes the binary point? Well, it doesn't. It's actually the way we declare and define numbers. And I'll get to that in a tick. Okay, so straight away we can see this has worked really well. And we can go the other way as well. We can convert a binary number back to its digital equivalent once again. And as always, we start with a number line. So we start with 1, 2, 4. That's all I need. Point. Now, do you want to do it as binary or as decimal or as a fraction? Fractions, excellent. Half, quarter, eighth. Todd, stop talking like that, please.
Why?
Because this is a stereo microphone and it recognises you're two different people.
What do you mean?
We sound exactly the same because we're the same person.
Yeah, really.
I'm so going to edit this.
Just leave us.
101.101. Okay, so 4 plus 1 is 5 and 5/8. Okay, it's dead simple. In an exam, if you were to be given one of these, all you should do is smile and say thank you very much. I would, if you do, when you do it, always draw your number line first. That is the beginning point of any of these, because even if you get the rest of it completely wrong, you've demonstrated some understanding. There's marks there for you. Okay, so that's all of that page. Now we've got to look at answering margins question, which is where do we know where the floating point is? Well, we don't. It's actually, well, we do. It's declared as part of a number system. And the one that we study in software design development is single precision floating point operators, which sounds really, really cool. And actually what it comes down to is it is. When you see one for the first time, you're going to look at it and go, yeah, right, no thanks. When I throw one at you that, if I was to say convert 506 and 385 512ths to a floating point operator, and you get it right, and there's a random combination of 32 ones and zeros, you'll think to yourself, yeah, that is actually pretty cool. Okay, moving on. So, a floating point operator is a 32 binary characters, 32-bit number that is defined the same way, okay? And it's in 3 sections, and this is almost always in the exam because there's a few ways that an examiner can trick you. So the first thing we've got to worry about is that when you're doing a floating point operator, you start with a sign bit, 0 or 1. Now we've already just discussed sign and modulus before, so 0 is considered to be what value, positive or negative? And 1 is going to be negative. 0 equals plus VE, 1 equals minus VE. All right, simple. 0 or 1. So you look at the first character. It's a 0. It's a positive number. It's a 1. It's a negative number. Simple. Now the next part is the exponent. And I've got to jump down here a little bit and remind you of how scientific notation works. Those of you doing science, this is just standard operating procedure, scientific notation. But if you don't do science, or you haven't done it since year 10, I've got to remind you. So just a reminder, one of the random factoids that we learn in science, that the speed of light is 300,000 kilometres per second. About. Yes, I do know the exact number. No, I'm not going to go there.
Go there.
299,792.452 kilometres per second.
See, you went there.
Okay. Which is, if you like, instead of 300,000 kilometres per second, it's 300 million metres per second, which is a silly number to try and write. So we write it as 3 times 10 to the 8th metres per second. Does that notation ring familiar?
I was doing it 2 periods ago.
Yes? Okay. That part is the exponent. Okay? That to the power of 8 is the exponent. Yes? No? Maybe?
I
Ebony,
don't understand
what an exponent is.
Okay, so instead of writing this chunky big long number here,
Yeah.
I'm writing all those zeros as 10 to the power of something.
Okay, so how does it relate to what we're doing?
Because what we're doing, I'm going to write a number as in this manner.
Does the exponent also have a signed bit?
Hold on. So if I was to do the speed of light properly, instead of 3 times 10 to the 8, it would be 2.99979.
That's a 2.
Thank you.
You're welcome. I'm definitely...
792,452 times 10 to the 8th metres per second, which is kind of stupid. But when you're looking at a number like this, like 300 million as 3 times 10 to the 8th, you get an idea of the magnitude and you actually see that number as being relevant and important.
Okay.
Now, when we do it with floating points, it's the same idea. It's 1.10101 times, it's actually 2 to the power of a number. So the exponent here is, the exponent I'm going to go with here is going to be always, I'm going to get this wrong every time, it's always, good, it's always 8 characters long. So it's 8 bits. And this is the part that gets everybody, because it's frustrating, because it's annoying. But when you think about it, it gives you a chance to render incredibly huge numbers or incredibly small numbers. The way it's worked out, it's 127 plus the exponent value. 127 is 11111. 111. 127 plus the exponent value. So if your exponent starts with a 1 in that 8th data bit, it's a value above 1. If it starts with a 0, it's a value less than 1, or between 0 and 1. Okay? So it's 127 plus the exponent value. And when I work one out with you, you'll hopefully get it. But that then gives us the exponent, which means this gives us an opportunity to render incredibly huge numbers, and I mean seriously, seriously big numbers, or incredibly small numbers, 0.0000, lots of zeros down, and still render a very accurate small number.
Can you do both?
No, it's one or the other. And the reason why it's one or the other is because of the last part. Now, I said this is a 32-bit number. So the mantissa is everything else. Why is it called a mantissa? I have no idea. I actually don't know where the word comes from. But I've already used 1 bit for the sign and 8 bits. This is not going to work. He says, flailing his hands around. I've used 1 bit for the sign and 8 bits for the exponent. So therefore the mantissa is the remaining 23 bits. 23 plus 8 plus 1, pretty sure, is 32. So the remaining 23 bits are the mantissa. Okay? And that's how every single precision floating point operator, 32-bit single precision floating point operator, is rendered. Every single one of them. So to answer your question, Margin, how do you know where the binary point is? You know, because it's defined as that. Now this is following an IEEE standard. I don't remember what number it is, but it's a floating point operator as defined as a standard. So don't need that anymore. That's just confusing.
If it's a 16 floating point, is every part just half?
Big
So
what?
if it's a 16,
They're not it's not defined. This is, so you know how the IEEE defines electrical standards and numeric standards? Okay, this is defined 32-bit standard. There is actually a 64-bit standard as well, and a 64-bit floating point.
what about 16? Is that
No.
nothing?
I don't believe it's ever been defined. Because there'd be kind of no point. Okay. So, I want to go through this with you, to work it out with you, and I've got a whole bunch of notes down here to work through. This is where now I actually really do need you to ask questions. because what I'm about to show you, I know, is really confusing unless it just goes like that and it goes snap and you get it. So remember what I said over here about the binary point. We can convert numbers to binary. We can convert non-whole numbers to binary. Let's actually start here for a second. So the way you work out an exponent, I can show you on this one, is really, really simple. Here's my binary point. I'll do it in red. Here's my binary point. I want to get to move the binary point there. Okay? How many jumps does it take? So I go step 1, step 2, step 3, step 4. And that means my exponent would be 4. Without overthinking it, does that make sense? Okay? And that would therefore mean, if you think about it as well, this number would be 1.01111011 times 2 to the 4th power, approximately. That's rendered slightly differently. But you get the idea? Okay? So that's how we work out our exponent. How far across do we move the binary point so we have 1 point something? And that's really important because it's always going to be 1 point something. Now that, because we have 1 point something, gives us a little cheat that we can use that makes our 32-bit number 33 bits long. And I'll come back and explain that in a tick. It's really, really cool. Very cleverly thought out. So at the moment, let's say I want to convert my usual number, 42, and 15/16. Now I can write that as a binary number straight away because I know 42 is 10, 10, 10. And I know 15/16 is 0.1111. Okay? So I know that is my number. And that's why I pick it, because it's a number that you can get to straight away. So first thing you can think to yourself is, well, hang on a second. Question 1, is this number positive or negative? Positive, so therefore the sign bit is going to be 0. My exponent is going to be 1, 2, 3, 4, 5. So I'm moving the binary point 5 steps. Okay, so my exponent equals 5, except it doesn't. What does my exponent equal? 127 plus that value that I shifted. So what's 127 plus 5? 132. What's 132 as a binary number? We'll figure it out. Yeah, we'll figure it out.
128 plus 4.
Okay, so
Oh,
let's go through there.
16.
Exactly.
I was
Okay.
expecting it to be harder than that. I was like, wait, no, that's it.
When I throw one up here, I'm going to make it difficult for you. Just so I'm going to throw something at you that is way beyond the scope of an exam. So when you look at it, you're going to go blind with ones and zeros. But once you figure it out, it's going to go hopefully like that. Snap.
Oh, it's 42. Wow.
1, 0, 1, 0, 1, 0, 0.1111. Oh, look, there we go. And now the floating point number is that. Okay, so, and this is just going through what I've just said. So there's our 15/16. There's my number. My sign bit is 0 because it's positive. So my exponent, because I shifted the binary point 5 steps to make it 1 point something, my exponent is 132. 132 in binary, as Todd just said, 128 plus 4. Lots of zeros and ones. So the mantissa is everything. Now, here's the fun part. In binary, the numbers that I can choose are 0 and 1. Okay? And you never have 0 at the start of this value. There is never a leading 0. It's always a leading 1. Now, if it's always a leading 1, we can assume its value, which means our mantissa is actually 24 numbers long. We only show 23 of them. Okay? Think about that for a second. Because
Absolutely no sense.
Because if we look here, I'll do it in blue this time. If we look at this, when I shift to get my exponent value, it's going to be 1.010101, etc., etc., etc. Right? It's always going to be 1 point. So if I'm trying to find the exponent for this value, 0.1. What do I know I've got to go to? I've got to go to 1 point something. So it's going to be there. So I count my exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What do I know about these leading zeros? They don't do anything. They can go. It's always 1 point something. Because it's always 1 point something, when I go to calculate my mantissa, it's everything after that point. And I can assume that 1 is there because there's no other choice for it. Okay? Does that make sense? Good. Yes?
So is the part in red your mantissa?
Correct.
And so would you then do, because we're doing positive numbers, 0, 1 point, then your exponent, then mantissa?
Okay, so when you shove it all together, yes. The mantissa is everything after that 1. So that was just my example one, so I'll get rid of that so as not to confuse us. So there is my number. That's my mantissa. So my exponent first up is 127 plus the number of times I shifted, which is 5, so it's 132. Mantissa is everything after that first 1. So it's, here it is, it's 0, 1, 0, 1, etc. Now, what I haven't put in here, and I must, and this is going to cost me marks if I was to put this into an exam, I've got to get to 23. I've got to have 23 numbers in my mantissa. So if I've got a bunch of trailing zeros, I've got a bunch of trailing zeros. So when I put it all together, I have a sign bit, 0 for 0 for positive, 1 for negative, an exponent, 132, which is because I stepped my my binary point 5. Pardon me. Now, if I was to go, I'll finish this first. And then I have the mantissa, the rest of it, which is everything after that binary point, 0, 1, 0, 1, etc., etc., and then count to 23 to get to that number of zeros. And that is a 32-bit floating point operator. It is an incredibly clever, really well thought out piece of kit because a 32-bit number is actually 33 values, has 33 values in it. Okay, now there are some special cases, and we'll come back to these, and I'll remind you of these. Defined value, okay? This is a defined value. And therefore, we need to know. Minus infinity. So we count down as far as we can go. The lowest value, minus infinity. 1, which means that we have a negative. Lots of 1s means that it's a very small number. And then lots of zeros. Sorry, it's a very large number and lots of zeros. Now, you should see here, I can actually make a number smaller than minus infinity. All I've got to do is put a value in the mantissa. And I've got a number smaller than infinity. Phil, I know I'm boring. I'm boring myself to sleep as well. It's been a long day. I'm going to start throwing these at you, and you've got to be able to deal with them. So this is minus infinity. If there is any value in the mantissa at all, this is not a number. It's an error. It doesn't, by definition, it is not defined as a workable number. We have minus 0. Remember yesterday we were talking about sign and exponent? Yeah. Sign and modulus. We have 2 values for 0. Minus 0 and positive 0. At least positive 0 looks like it's going to be a 0. And there's also positive infinity. Okay? And again, any number in the mantissa. So really, any number in the mantissa, when the exponent is full of 1s, is an error. Okay? Simple as that. Any number in the mantissa when the exponent is full of 1s is an error. And that is because, by definition, these are the values that we have to have. Any value bigger or smaller is declared not a number. This Jen Cooper is awesome is because when I wrote this first time around, I gave her an absolute cracker of a number to work out, and she worked it out. Okay, so It's actually quite simple to do. We're going to do a couple of examples up on the board now.